Systemic racism remains a pervasive issue in America, and Virginia is no exception. With historical injustices contributing to disparities in education, housing, unemployment, and criminal justice, marginalized communities, especially Black and Indigenous populations, face enduring barriers to equal opportunities. Addressing this issue necessitates sustained efforts to dismantle discriminatory structures and foster a more equitable society. So we chose to tackle the problem of systemic racism in Virginia through an analysis of income predictors among Virginia residents. Machine learning allows us to make highly tuned inferences about the nature and form of income-based discrimination, as well as provide targeted solutions and explanations. So the first thing we did was find a data set that could help us. We found a data set with socioeconomic information for individuals in Virginia that was perfect for our project's goals. The data had race, age, work class, education, marital status, occupation, relationships, sex, and hours per week as its features, and its target is annual income of either greater than 50K or less than 50K. After some data pre-processing, we first decided on a logistic regression model as our initial data set reduces a binary classification problem, where the probability of an individual making greater than $50,000 a year was evaluated by the model. Our preliminary model had an accuracy of 0.8366 with an F1 score of 60.63. Thus, there was room for improvement. A more detailed analysis of this logistic regression's performance yields the following confusion matrices. The logistic regression algorithm was suitable for initial experiments, as we can perform a feature importance analysis simply by inspecting the coefficients learned by the model. By extracting the model coefficients for each racial class, we can get an initial estimation of how and to what extent the different races play a role in projecting financial success. We can see from our initial results that other and American Indian Eskimo hold negative values, indicating that these groups are negatively correlated with expected income. We also see that the Black group holds a low positive value of 0.03, significantly lower than white.
We then decided to extend our experiments by using a more contemporary model. We decided on a network architecture with 176 input dimensions after hot-encoded features, a hidden layer of 256 neurons, and an output vector of 2 neurons, denoting the hot-encoded classes. We saw that this network rapidly learned the features in the dataset and maintained a significantly higher average F1 score of 0.84. In order to take advantage of the insights learned by this model, we first had to figure out how to interpret the inference structure of our neural network. This was more difficult than using a logistic regression, as we weren't able to simply interpret the coefficients of the model the same way. We thus first came up with a method that involved sampling from the distribution of validation data and manually augmenting the racial breakdown of each example. We realized that setting the validation data into 5 groups determined by each artificially augmented group resulted in 5 distinct distributions of income probability. We then binned this data into histograms and used a kernel density estimation technique to obtain a continuous distribution with respect to probability. We obtained the following continuous distributions, indicating some interesting properties. By simply taking the mean of these distributions, we essentially get the mean predicted score for each racial breakdown, which we can see on the right here. Here we see a similar distribution to the one obtained by the logistic regression. However, these results don't align closely with expectations. Firstly, the Asian Pacific Islander group presents itself as the most advantaged group, while the Black and other are relatively close to the white group. From inspecting the distributions, we see that not all distributions are created equally here. The model learns that the distributions in the American Indian Eskimo and Asian Pacific Islander cases have bimodal properties, around 0.7 and 0.6 respectively. We thus turned our attention to the more representative modes underlying these distributions, outlined with these black lines here. By obtaining adjusted income class probability statistics, we found results that more aligned with what we were expecting. We saw that by far the white group was the most advantaged, with its central mode being at least 0.2 higher than the closest group. We also saw that Asian Pacific Islander and Asian Indian Eskimo were now the most disadvantaged group, satisfying our little mystery. We would finally like to mention what the impacts are and implications are of our model-based approach. If we simply inspect the dataset and count the number of data entries that correspond to the relative classes, we obtain this proportional breakdown with respect to the different groups. What we see is, once again, a breakdown that is extremely inconsistent with our expectations, where the Asian Pacific Islander group is once again overrepresented in income. This sort of breakdown reveals little about racial issues, as it ignores the complex structure that exists in Virginian societies and all the data present in our sets. The lessons we learned from these experiments were firstly that not all distributions were created equal. There is more information to be gained from analysis than simply some summary statistics of means. Additionally, we could use the discrete classes in our dataset to obtain continuous probabilities that lended themselves to more in-depth analysis. Finally, there were certain improvements that we noticed during our experiments that we could make. Firstly, we could maintain a stricter distribution of target labels, ensuring that income classes were equally represented in the data, as well as an even distribution of different races, whereas roughly 90% of our dataset included white individuals. We also could improve our experiments by using more features, more examples, and more detailed racial breakdowns extending outside of groups like other. We could also turn this into a regression-based problem instead of a classification problem, using continuous income labels. This would require detailed data. Thank you.